Hi everyone, welcome again to day 5 of Just Start Programming, learning the Rust programming language. Alright, so the other day we stopped at the slice type. So let's just go through quickly, do a quick recap of what is this slices. Slices lets you reference a continuous sequence of elements in a collection. So just like this one. So first word is a function, and then you have a reference of a string type, parameter, and since we don't need ownership, so this is fine. Here's an example. So we have first word s with a reference to a string type that returns a usize. S, where it gets the explanation is here. To an array of bytes using the asBytes method. So asBytes would return an array of bytes. Next, we create an iterator over the array of bytes using the itr method. Okay, so enumerate is a function call that wraps the result of the iterator and returns each element as part of a tuple. First element of the tuple returned from enumerate is the index. Second element is a reference to the element. So this is the tuple that is being returned. So the first one is index, and then the second one is the reference to the element. Okay, because enumerate method returns a tuple, we can use patterns to destructure that tuple. Okay. Inside the for loop, we search for the byte that represents the space using the byte literal. Okay, so this is the byte literal. If we find a space, so this is the space, we return the position. Otherwise, we return the length of the string by using slen. Return I. So I is the position. Otherwise, it will return the length. We now have a way to find out the index. But there's a problem. We are returning a usize on its own, but it's only meaningful number in the context of at string. In other words, because it's separate from the value from the string, there's no guarantee it will still be valid in the future. Consider the program. First word, hello world. Okay, word will get the value 5 from this 0, 1, 2, 3, 4, 5, and then space. But we have s.clear. This empties the string, making it to equal to this. So word still has the value 5 because the return of first word is s.len. No, that will be the index. Yeah, it will be the index. But s no longer has any content. that we could meaningfully use with the value 5. So word is now totally invalid. Let's run this and see. No output. This program compiles without any errors and would also do so if we use word after calling sclear, because the word isn't connected to the state of s. Word still contains the value 5. We could use that value 5 with the variable s to try to extract the first word out, but this would be a bug because contents of s have changed since we saved 5 in word. Having to worry about the index in word getting out of sync with the data in s is tedious and error prone. Managing these indices is even more brittle when we write second word function. Its signature would have to look like this. Okay, so I think the point was, luckily Rust has a solution to this problem. We can use string slice. Okay, I think that's the main point. So we can do something like this. So it looks more convenient. So if you want to extract hello, you can have immutable hello referencing s, which is also immutable, from 0 to 5. So 0 to 5. 0, 1, 2, 3, 4, 5. And then world referencing 6 to 11. 6, 7, 8, 9, 10, 11. Rather than a reference to the entire string hello, is a reference to a point of the string specified between 0 to 5 bit. We create slices using range within brackets by specifying start index, ending index. Start index is the first portion in the slice, and ending index is one more than the last position in the slice. So I think that explains why it's 11. Because if we start at 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's only 10. But it says here it should be one more than the last position in the slice. So it should be 11. Internally, the slice data structure stores the starting position and the length of the slice. Okay, internally, which corresponds to ending index minus the starting index. So in the case of let world s to 11, world would be a slice that contains 11 minus 6 with a length value of 5. Okay, with Rust's dot range syntax, if you want to start at index 0, you can drop the value before the two periods. In other words, these are equal. Okay, the same. By the same token, your slices includes the last byte of the string. You can drop the trailing number, okay, like this. You can also drop both to take the slice of the entire string, like this. Or you can just do %s, I would say. No need to do something like this. Why don't we try it out? Oops. I think this was from yesterday. Maybe we can continue from here. S equals string colon from below below equals to a reference to S, and if we print line below, should be okay. Should be okay. We can comment this out. We can also comment this out. Yeah, so they're the same. Low value. Okay, so let's continue. With all this information in mind, let's rewrite first word to return a slice. The type that signifies string slice is written as ampersand str. Okay, so it takes an array of bytes stored here. Bytes will return an iterator, and iterator calls enumerate, which makes it into a tuple where the first element would be the index, and then the second element would be a reference to the value. So if item is a space, it will return a reference to 0 until the index where space is found. So it will return a reference. So assuming that this is hello world, then this part will return world. Okay, then how about this one? So if it comes out of the loop and if there's no space to be found, it will just return the entire string, a reference to the entire string. Okay, so let's see what's the explanation here. Get back the single value that is tied to underlying data. The value is made up of a reference to the starting point of the slice and a number of elements in the slice. Okay. Now we have a straightforward, okay, this one is returning a slice would also work for the second word. The second word. This first word. Second word. Okay, there was no implementation. Let's see. Okay, second word. Ensures the references into the string remain valid. Remember the bug in the program in listing 4-8 when we got the index to the end of the first word but then cleared the string. So our index was invalid. That code was logically incorrect but didn't show any immediate errors. The problems would show up later if you kept trying to use the first word index with an empty string. Slices make a bug impossible and let us know we have a problem with our code much sooner using the slice version of the first word that threw a compile time error. Okay, because inside first word, the implementation looks like this, where you have slice from index 0 to the index where space is found, which is a reference. So if we compare this to the first implementation, so this one is just the index. It's the index. There will be an error here. It's the explanation. Okay, cannot borrow s as mutable because it is also borrowed as immutable. S is mutable, so it was borrowed here, but it's referencing the value. Then word is immutable. Okay, yeah, so word is immutable. When you do s.clear, yeah, so s here, you're actually changing the value of mutable s. But why is it throwing an error? While word is borrowed later and used here. Okay. Recall from the borrowing rules that we have an immutable reference to something. Okay. We cannot also take a mutable reference. Okay, so word is a mutable reference to something. Why? Because, let's see, first word, okay, because it returns a mutable reference to something. So what is returned? Okay, so, no, it's not mutable, but it's a reference to something. So it's a reference to something. It's a reference to something, which is immutable. And then S, you have a reference to a mutable. Yeah, it's a reference, but S is mutable here. Okay, so if have an immutable reference to something, we cannot also take mutable reference because clear needs to truncate the string. Yeah, so clear function is to truncate the string, which is hello world. Okay. It needs to get a mutable reference. Okay, so it needs to get a mutable reference, but it's a reference, but it's not mutable. I think I remember there should be a mut over here. Where was that? Okay, we can try it out. Let's fix this issue and see if we can fix it. So let me just copy this, put it here, maybe delete everything. Okay. Save it first and check. Oh, first word is missing. First word is missing. So let's copy the implementation of first word. Copy. Here. Insert. Control V. Okay, so first word is here. Okay, so here we can see there's an error. Truncates the string, removing all contents. While this means the string will have a length of 0, it does not touch its capacity. Let's see how we can fix this part. First word, about if we put what? Is it correct? Remove this mut. Variable does not need to be mutable. Mut can be used in several situations. The first is mutable variables, which can be used anywhere you can bind a value to a variable name. Okay, so it's not needed here. Can we fix this? It's not needed. Where did we see that mut reference? Maybe let's go back to references and borrowing. Yeah, something like this. Ah, mut should be like this. Okay, let's try that out. So that mut string, then over here put mut also, right? But not s. Okay, so what happened? Cannot borrow s. S mutable more than once at a time. Okay, so now we have another error. First mutable borrow occurs here in line 4, 27. Okay. Yep. Go to string. First borrow later used here. $8.34. If we comment this out, of course, should be fine. Why I cannot clear string? Let's put it back. Let's put it back and go through the explanation again. So there's an error. I borrow s as mutable because it's also borrowed as immutable. Mutable borrow occurs here. Immutable borrow later used here in Word. Okay, so when it goes here, we are already borrowing. So S is no longer valid. S is no longer valid. But we can use S here. S clear. I think here we can do this one. Yeah. And word should be empty. In this case, clear is allowed because this is mutable. So in effect, once we get into first word, referencing string S would be empty. So although it's checking it as bytes, so it will not go through this one. Eventually it's empty, then the reference will go, it will be empty. Then word would be empty. Yeah? I hope my understanding is correct. So it should work and it will be empty. Empty. All right. So that is just to verify and understand that without this slice type, yeah, I mean, to me, it's quite difficult to recreate all of this. I would rather use something like this. Hello world, it's quite easy. Let's copy this. Oops. What did I forget to copy? Ah, okay. Hello world. Then if we print, hello world. World semicolon. So far, what I have mastered is to type in the print line, but that's all right. We'll do this step by step together. Okay, so it should be hello world. If I remove 5, so hello would be hello world and world would be world. Hello world world. Yeah, I put a comma here, then it will be clear. Hello world world. Okay, if we can remove this also, since we are practicing the string slice. Be hello world world still. Okay, then we can remove this further. It's going to be hello world world. Yes. Okay, I think the interesting thing is the how we count the index. It should be the last word plus 1. So if we make this as 10, so you only get hello world world. Okay, so that's how we use slice types in strings. Okay, so this is just a review. Okay, I think there's another one where we have slice types for array. Where was that? My string, first word, my string. First word works on slices of strings, whether partial or whole. Okay, so this is immutable. We have a reference to my string from 0 to 6. So that's hello. It could be, yeah, these two lines are the same. Works on references to strings which are equivalent to whole slices of strings. Okay, so it will also work on my string, string literal. Okay, now I remember. I think the point here was when the first word function was revised to where was it? This one. So you can pass references to string or slices of string, references to string itself, and it can also be used for string literal, like this, which makes it more flexible. So you can do something like this also. Okay, so there are other slices. String slices, as you might imagine, are specific to strings, but there's a more general slice type too. So we have an array here. So you can slice the array. We take the reference to the array, and then from 1 to 3. But this is 1 to 3. Array starts at index 0, so 0, 1, 2, 3. I think it will print out 234. Okay, so let's try this out. Let me just copy this to go back here. You can just append it here. And then do another print line. So I'm an expert in calling print line slice. Hey, what's wrong? Slice. Why you cannot print slice? One, two, three. Oh, I retract my statement. I'm not an expert in using print line. Okay, but let's try to fix this. Doesn't implement format display. Display is not implemented for integer. Okay. So in format strings, you may be able to use this or pretty print. How to use this one? Colon question mark or colon sharp question mark for pretty print. Colon question mark. Yeah. No. Okay. Maybe we need to look for an example how to print Rust programming language printing integers formatted print. Okay, by example. Let's see. Paste. Okay. So let's try. Okay, let's remove slice here. Let's put something here. The slice equals. Let's put a comma. Slice. Okay, quick. It's not implemented for because it's array of integers. Okay. We have something here for array of integers. Nope, we don't have. So can we do? Maybe let's use our for loop. Let's see if we can remember for loop. For num this is num slice for num in slice, something like that. Okay, so slice this should be num. Okay, will this work? Let's remove the extra space here. Ah, correct. So it printed out 2 and 3 because it's index 0, 1, 2, and 3. Remember, it should be the last index plus 1 because eventually the size would be 3 minus 1. So 3 minus 1 is only 2. That's why we only have 2 elements here. All right, so I hope you're with me. I hope you understood something from this. If not, you can just rewatch everything and try it yourself. You can pause the video once this is finally uploaded as a replay. Okay, so let's move on. So here, summary concepts of ownership, borrowing, and slices ensure memory safety. In Rust programs at compile time, the Rust language gives you control over your memory usage. Excellent. In the same way as other systems programming languages. But having the owner of data automatically clean up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Amazing. I'm beginning to like this feature. No extra effort except that before you code or you write your program, the compiler will ensure that there won't be any dangling pointers and everything is cleaned up once it goes out of scope. Ownership affects how lots of other parts of Rust work. So we'll talk about this concept further throughout the rest of the book. Okay, so now it's time to move on to one of the most exciting part, which is struct. Let's see. Using structs to structure related data. A struct or structure is a custom data type that lets you package together and name multiple related values that make up a meaningful group. If you're familiar with an object-oriented language, a struct is like an object's data attributes. In this chapter, we'll compare and contrast tuples with structs to build on what you already know and demonstrate when structs are a better way to group data. Okay, so if you don't understand what object-oriented language is, I think it's better if there's an explanation here. If I'm a beginner, then I wouldn't have any idea what this is all about. Okay, so without understanding object-oriented language, I still believe we can program by just going through the next pages of this book. So let's see. Let's continue. Structs are similar to tuples. So the other day we have gone through this tuple type section. In that both hold multiple related values like tuples. The pieces of a struct can be different types. Unlike with tuples, in a struct, you'll name each piece of data so it's clear what the values mean. So in tuples, you go by the order. Like for example, from what I've learned, tuples will look like this. So this one could be a number 1, and this one could be another number, and this one could be a string. So this is a tuple. But here, later on, you can have another tuple which is string, then here it could be a number, and this could be another number. Yeah. So you go by the order, and how you reference these parts, how you break it up is you have that dot notation. How do we do that? Let x, y, z. This is going to be confusing. Yeah. So if we look like this, automatically the Visual Code Editor added the data type, or is it suggesting these data types? I did not enter these. So we can try that outside also. Outside, I mean from the terminal. So open up that code again. Yep. So you see, I'm clueless what x is. Yeah, but from here at compile time, x takes on the data type, which is a string literal, and y takes is it I32 or U32 by default? I32 by default. So unlike tuple, what's nice about struct is you can name where was that? Yeah, here. Unlike with tuples, in struct you'll name each piece of data so it's clear what the values mean. To define struct, enter the word struct. It's a keyword, and name the entire struct. Name the entire struct. So here it's name user. Struct user. A struct's name should describe the significance of the pieces of data being grouped together. Then inside curly brackets, so the curly brackets, we learned that this will define the scope. We define the names and types of these pieces of data, which we call fields. Okay, names and types of the pieces of data, which we call fields. So these things are fields. So here it is named as active Boolean data type. Okay, so if you notice, there's no let keyword here. So I think that is one of the difference. Shows a struct that stores information about user account. So user will have active, user will have username, user will have email, and user will have sign-in count. Data types are Boolean, bool, string, also string, and U64, and signed integer 64-bit. To use a struct, after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct and then add curly brackets containing key value pairs. So key and value pairs together, where the keys are the names of the fields and the values are the data. Okay, we want to store in those fields. We don't have to specify the fields in the same order in which we declare them in struct. Okay, so there's no strict rule that it should be active username, email, sign in count. Okay, but here it's in proper order. We will test that out. Let's see if it's true. And the values are the data we want to store in those fields. We don't have to specify the fields in the same order, okay? In other words, the struct definition is like a general template for the type. And instances fill in that template with particular data to create values of the type. For example, okay, so here, user, okay, user. Create an instance specifying complete value, okay? We create an instance by stating the name of the struct and add curly brackets. Name of the struct, user, adding curly brackets over here. Oh, there's a slight difference. Here, when we instantiate, we have semicolon here, but when we define the struct, there's no semicolon. Okay, so there's a slight difference. Okay, then that means that this becomes an expression. So user is binded to let user1. So user1 is, there's no mut here in front, so it's not mutable. It means it's immutable, meaning the value cannot change. And then you have the key value pair. So here they look similar. It means that you use the name, the key, and then instead of data type you substitute the value. Okay, so for Boolean it's only true or false, so here it's true. Username, so it's a string. Okay, so string from string literal. Okay, so in this case, lines like this are like binding true to the variable active, something like that. That's how I would interpret it. Binding this to variable username, binding this to variable email, binding one to variable sign in count. Okay, so it's like you have a let statement here, but slightly different because we treat this as key, then the value, key value. Okay, maybe we can try this out. Oh, I did not say where we can put the strut. Let's make a new project and try this out. So here, what I will do is, instead of slice, so we do this together once again, creating a new project, cargo new. Maybe we can name this as structs. Okay, then we will do a cd, change directory to structs, and then do a tree just to check if we have everything in place. So you have cargo, tamang, source, and main RS underneath the source. Then we can view, or we can VI source main. We don't need to do that. We can also cut source main. Yeah, hello world. Then from here we can open Visual Code. So code dot. Then let's close the other instance of this one. So let's start fresh. I'm going to copy this. Okay, so maybe I can put it somewhere below. I don't know if that's a good idea. Then step down below world. Maybe we can copy this. I think we have some warnings. This is unused variable, that is fine. Here, never read. Okay, maybe we can just ignore that. So user 1 is unused. Okay, let's use it using line and user 1. Will it work? It didn't work for array. Here it will not work as well. Yeah. Can we do user maybe dot active? Will it work? Oh, this will work as well. Maybe parenthesis. Expected, intended to print. You can escape it using. Let's do quick fix. Okay, so active is not a method, so we can remove this. There. But now we need to do the same for username, email, and sign in contact. Copy this entire line, paste it here. Username. This one is email. And sign in contact. Sign in com. Okay, no more warnings. Let's run. Alright, so true. Someone username. Someone at example and 1. Okay, so I'm just guessing, by the way, how to access. As you can see, I don't know what's the correct one, but just trying my luck. So active, username, email, sign in, count. Okay, let's continue reading the book. Okay, to get a specific value from struct, we use dot notation. For example, to access the user's email address, we use user1 email. I was right. If the instance is mutable, we can change a value by using the dot notation and assigning into a particular field. Let's see. Okay. 5-3. How to change the value in email field of a mutable user. Now you see there is mutable here, so you can change. But having it here, it means you can change everything, not just email. Anyway, let's try it out. Okay, here, user 1. Let's make it mutable. So that we can change user 1. Then here, user 1 dot email equals email is string. Okay, so string from somebody example.com. Okay, so if we run this, oops, something's wrong. Expected value found struct string. Okay. So it shouldn't be dot. It should be colon. Means we are accessing the function from string. Correct. So let's run this. Somebody. So somebody changed. Okay, so that's how you change it. But the significance of mat here is if you remove this, then it will complain. Yeah? Because user 1 is immutable, meaning you cannot change it. So it will be fixed, and by changing it is not allowed. So whatever you do, the compiler will not let you change it. It will only work if you comment this out, then you print out this one. So it's like the compile time, it's static or hard-coded values. Okay. Note that the entire instance must be mutable. Yes. Entire instance must be mutable. It seems like we cannot do partial mutability. Rust doesn't allow us to mark only certain fields as mutable. As with any expression, we cannot construct a new instance of the struct as the last expression in the function body to implicitly return that new instance. Using 5-4 shows a build user function that returns a user instance with a given email and username. The active field gets the value of active, okay, true, and the sign-in count gets a value of 1. What does it mean? We have a function build user. Okay, you have an input parameter email, which is string data type, and a username with string data type. It will return user, which is a struct. Okay, so in Rust, you can just simply ignore return, but as long as you can put the value or the variable here straight away. So user, okay, so I think this is how you create structs. Yeah, similar to this part without the semicolon. Okay, when you ignore the semicolon, then it will take this as the return value. Or perhaps you can do a return and then you put a semicolon. Yeah, maybe we can try that out. So let's copy this. It's faster to copy that one. Then maybe I'll put it here. Insert, Control V. Okay, so there's a warning, meaning build user is not used anywhere. So it's a waste of stuck memory. About here, build user, we call build user, maybe let user2 equals build user, where email is, what shall we put? It's a string. Can I do something like this? Batman at com.bat at bat.com, maybe something like that. Username Batman. Okay, and then maybe we can copy this line and put it here. Instead of user 1, so user 2. Okay, there's an error. Build user. Expected string found str. Okay, so what is wrong? String. Okay, so maybe we need to do something like maybe we can do string colon from, like this. Okay, do this. And here string colon from this. Okay. And here, yeah. Let's save. Let's run. There. So user2, is user2 active. Username true, batman at bat.com. Signed in count 1. So what does it mean? We can create a function like this, return a user, where you can accept 2 parameters, and then you can predefine the value, and you can pass the parameter here. Okay, let me just verify something else. If I print this again, so this should complain. Oh, did not complain. Why? We have already used user2. That is strange. Maybe again. Split again. I thought, okay, although user2 is immutable, it's immutable, but here, okay, so we are changing it the first time. And then after using it, it should be already out of scope. Well, I can print it here again. Did I miss something? Okay. Okay. Maybe let's just continue. It makes sense to name the function parameters with a name as the struct fields, but having to repeat email and username field names and variables is a bit tedious. If the struct had more fields representing each name, would get even more annoying. Luckily, there's a convenient shorthand. Okay. So it was the shorthand. Because the parameter names and the struct field names are exactly the same, we can use the field init shorthand syntax to rewrite build user. So it behaves exactly the same but doesn't have the repetition of username and email. What has changed? Okay. So here, username, email. Okay. Because what we have done here, email is email, username is name. Usually what we do is to distinguish this, maybe some naming convention, we put p underscore email, and this one is p underscore username. This one is p username, p email. Just to indicate that it's a parameter. But in this case, you don't need to do it. Not even indicating that it's a parameter. According to this book, we have the shortcut username comma and email comma. It's quite convenient. So we can remove this instead and just retain exactly what's in here. So it will still work. Yeah. So how about if we change it to p email, p username, here p username and p email. It will not work. Why? I think, okay, so it's using the struct naming convention. So it follows the struct. So we remove this, it'll complain. Because now this one doesn't have any value. Cannot find value username in this scope. Okay. Shortcuts. It's good if you have shortcuts, but I think readability wise, for reading the program, I think it's quite confusing. Yeah. Yeah. So I would rather, I don't know, it's just a preference. I would rather put in P email here, P username here. It's quite ugly. I'm quite sure that I'm referring to those values. What do you think? Okay, but this is Rust. This is Rust. Let's keep an open mind. Let's remove this and do it the Rust way. For sure, there's a good reason for this. So let's use the shortcut. Username, email. Right. Okay. Yeah. Creating instances from other instances with struct update syntax. It's often useful to create a new instance of a struct that includes most of the values from another instance, but changes some. It's often useful to create a new instance of a struct that includes most of the values from another instance, but changes some. You can do this using struct update syntax. Okay, so this is, previously we had shorthand. Now we have struct update syntax. Okay. 5-6. Create a new user instance in user2 regularly without the update syntax. We set a new value for email, but otherwise we use the same values from user1 that we created in listing 5-2. Snip. I think this is a code snippet. User2 user1.active, user1 username. Okay, and email string. Okay, this we understand. This one, however, is something new. So it's like I'll use user1 as a template. So whatever value I have in user1, I'll have the same value here as well. Okay. Using struct update syntax, we can achieve the same effect with less code, as shown in 5-7. The syntax ... specifies that the remaining fields not explicitly set should have the same value as the fields in the given instance. Okay. Specifies that the remaining fields does not explicitly set, should have the same values as the fields in the given instance. Okay, let's inspect this. Okay, let me copy user2. Where's my user2? Okay, so I'll remove this line. Let's skip that one. Let's remove this line also. Let's insert this. Okay, user2. Let's try this one first. So user1, it's over there. We can use user1 as active. Let's print this one if it works. Okay, so it works. That one works. So let's try the other one. Struct update syntax. Okay. Oops. Okay. Oh, why does it complain? Because now user2 is already here. It's not allowed. Copy. Cannot do that. User1. Okay, so we print this. Run. Yeah, so it worked. Another, because of this. Okay, I want to use another. I want Batman, that cop. Yeah, user1. So it's a shortcut. Shortcuts are nice, but there's missing information. So somehow you need to know that, okay, you need to know the concept that this means I don't want to change everything. I can still assign it to user2 by using the values from user1 except email. Say for example, I want to change the name also. Name, no, username, and string from. Now I'm an expert in creating strings. Batman. Yeah. Okay, that's clear. Where were we? Shorthand, struct update syntax, and then okay, so this is the explanation. User2 has a different value for email, but has the same values for username, active, and sign-in count fields from user1. The dot user1 must come last to specify that any remaining fields should get their values from the corresponding fields in user 1. But we can choose to specify values for as many fields as we want in any order, regardless of the order of the fields in the structs definition. So you have some form of flexibility, but this one has to come at the very end. So there's a meaning. Okay, let's test it out. Challenging the code to move this somewhere else. Okay, let's put it here. Yeah, so straight away it complains. It complains. But I think it would be better if there's a quick fix also. Then it says that you can rearrange this, it here, and it will still work. Yep. Okay. Note that the struct update syntax uses equal, like an assignment. Like an assignment. Where's the struct update syntax? Or is it referring to this one? Like an assignment. This is because it moves the data just as we saw. Okay, this is in the previous chapter. So struct moves the data into user 2. We can no longer use user 1 after creating user 2. Can no longer use user 1 after creating user 2. Let's see. Let's test it out. Let's copy it here. And instead of 2, let's change it to 1. There's no error. It's strange. It's a move. After creating user 2, because a string in the username field of user 1 was moved into user 2. If we have given user 2 a new string values, both email and username, and thus only use the active and sign in count values from user 1, then user 1 would still be valid after creating user 2. Both active and sign in count are types that implements the copy trait. So the behavior discussed, stack only data copy section would apply. You can still use user 1 email in this example because its value was not moved. So it seems like there's an exception because, okay, so that explains why user 1 is still not freed or not garbage collected, because it implemented a copy function by doing this. So okay, so this part is a bit confusing. So it's like, we comment this out, and then let's do that user2 equals user that's that active plus you. It's already there. Let's comment this out. So according to that statement, because email and sign in count no active and sign in count, active and sign in count uses are types that implements copy trait. Okay, so what does it mean? Active and sign in count are types that implement the copy trait. So what we have learned in the previous day was that active is actually a scalar type. Active is Boolean, and sign in count is also scalar, which is integer, unsigned integer. However, string is special. It's not scalar. And scalar types, when you assign them to another variable, it will automatically create a copy. It will create a copy. So it's like you're copying the values. And since this is inside a struct, it will assume that any other field inside the struct will do a copy function as well. No, not a copy function, but it will copy the value. Okay, so that's what I understood from that previous statement. So it means that's the reason why user 1 did not go out of scope. What is this? So in this case, there's an issue. Username, which is not a scalar, now it complains. It doesn't implement the copy trait. Okay, so if we comment this out, then email will complain. What? Email. Oh, we did not copy it. We changed the value of email, or we assigned a new value to email in user 1. Okay, but if we do it like this, user 1 dot email, it should be fine. Yeah, no, it's the same as username. So eventually you are copying it, but string does not implement the copy trait. So this one is not allowed. It's only allowed for scalar types, which is Boolean, and then integers, or if it's string literal, I think it should work. But string here is, I don't know how should we call this. I think, let's see, it's not name. String is okay, scalar or statically typed language, and then the other one is what was the term? Floating point, numeric operations, Boolean type, character type, compound types. No, compound type is tuple. Array type. The two data types. Where are they? Statically typed language, which is known at compile time. Character type, compound types. Where is that? Data types. Scalar and compound. Okay, it's here. Scalar and compound. So maybe string is compound. Yeah. Let's get back to where were we? Okay. Both active and sign-in count are types that implements copy traits, so the behavior we discussed in stack-only data copy section would apply. We can still use user email in this example because its value was not moved out. Its value was not moved out. What was the original code? Email. I'm a bit lost. Okay, let's revert it back. Let's comment this out. So this should be valid. So it says we can still use username, email, active, and sign-in count because we did not do a move, but I think we created a new email here and username. And user 1 is still okay because aside from email and username, these are scalar data types. So it automatically implements the copy trait. So it was able to copy it. So it's like user2 is something fresh, and user1 is still available, even though we created a new struct and assigned it to user2. So the value of user1 active is actually copied to user2 active. And the value of user1 sign-in count is copied to user2 sign-in count. So two separate values, two separate locations in the memory. So both in stack. Okay. Let's move on. Using tuple structs without named fields to create different types. Rust also supports structs that look similar to tuples called tuple structs. Tuple structs. Tuple structs have the added meaning in the struct name provides, but don't have names associated with their fields. Rather, they have the types of the fields. Tuple structs are useful when you want to give the whole tuple a name and make the tuple a different type from other tuples. And when naming each field, as in a regular struct, would be verbose or redundant. So you don't need to name the field, as tuple follows certain order. But it helps to name the tuple in order for you to differentiate the different tuples. Okay, so here, although it's a struct, but it looks like a tuple named color, which takes in I32 data type, scalar data type, color. So maybe this is RGB, red, green, blue. And then point, maybe XYZ of the coordinate. Main, and then you have color 000, and then origin point 000. Okay. Okay, understood. So it says that even though if you put the field name here, probably R colon I32, it's already redundant or verbose. You don't need to name it. Note that the black and origin values are different types because they're instances of different tuple structs. Each struct you define is its own type. Even though the fields within the struct might have the same types. For example, a function that takes a parameter of type color cannot take a point as an argument, even though both types are made up of I32 values. Okay. You cannot interchange them, although they have the same data types. 3 I32 values. Otherwise, tuple struct instances are similar to tuples in that you can destructure them into their individual pieces, and you can use a dot followed by the index to access an individual value. Unlike tuples, tuple structs require you to name the type of the struct when you destructure them. For example, we would write let point xyz equals point. Okay, let's try this out. Copy this. Maybe we can just reuse this one and then just define a struct over here. But remove main, and let's move this somewhere else. So black and origin, they're not used. So if I put color, maybe R, it's G, it's D. Uh, oh, we cannot even put in something like this. Okay. So we cannot name it because they were saying it was redundant. Okay, then let's remove that one. It's here. Then we access equals dot 0. Maybe I'll put a number here. Maybe uh, 2. R equals to 0. Yeah, so that's how you access the first value in tuple. Okay, let's see what else is here. Name the type of the struct when you destructure them. Point. That point equals to point. For example, we would write let point xyz equals to point. Then why do we have a dot here? Oh, this is part of the sentence. Okay. Let's do another one here. Let point. This is how you name it. X, Y, Z equals to point. Okay. Let point. Then how do we use XYZ? Okay, point will complain. Can we do something like this? 10, 20, 30. That work? No. Quick fix. There. got point. Point 10, 20, 30. It means, can we change this to point? Yes. Point. A tuple struct with a similar name exists. Don't understand it. Why this one is point, capital P. Okay, and then how do I use this? Print point equals point. Is that correct? Point at x. Point 1. Point 1. What? This right hand side is the struct. Okay. Stood, but analyze this. Point what's the variable? Location. Do something like this. What? This is confusing. This one works. Point. Does it mean that what's this point? Origin. Can I comment this out and then here let me put origin colon. We already did that. What? Can I find type C in this code? And how do I use that one? Let's go back to the book. Is there something missed? Unlike tuples, tuple structs require you to name the type of the struct when you destructure them. But why do we have point here? Okay, okay. Let's see. If we remove this, I put origin here. Okay, comment out this one, and that should work. So how do I print point X? Let's see. I do point dot X here. Oh. Point X. Oh. No field X on type. No field X. Point 1. Destructure the tuple. Location. What? Quick fix. Okay, angle brackets and then uh, 0. Yeah, I know that will work, but how do we use that one? Dot X. Unknown field. We need more examples. Okay, let's search. Or is there something here? This one I don't understand. The structure struct tuples. Example. See how to destructure a tuple struct. Oh, okay. Trying to understand destructuring a tuple struct into primitive variables. Okay, so we have this origin. Let HWD origin. Okay. Okay. Goal here is to recreate HWD as individual I32 variables. Any hints? Constructor syntax is designed to be symmetric with pattern. What is this? Let at x equals to, okay, let ABC equals to 789, let foo, let point, okay. So this is what you want, let origin equals to, let origin equals to 0.000, yeah. Then let point HWD equals origin. Okay, origin. That's what I'm doing here. And origin or can it be, oh, I think I've already tried point dot x. No field x on type. Okay, but if I do origin, no field x on type point. Okay, I'm not sure, but did you try it out? Let point, okay, okay, let's see. Pattern syntax. Oh my, this is already chapter 19. We gather all the syntax that is valid in patterns and discuss why and when you might want to use each one. This is quite advanced. I think before we get here, we need to understand what match is. Let's see, from here, let ampersand x equals to ampersand 42, ABC 789, var. Yeah, I did that. Yes, of course. There's no error. Okay, I added print line origin. This is what you want. This is what you want. Copy. Because I wanted to use those values here. Okay. Don't want new line. X, Y, Z. X, Y, Z. Yeah, this is what I want. So what happened here? What happened here? X, Y, Z. It will print, sure. Yeah, X, Y, Z. For sure it will print X, Y, Z. But how would I specify that this is XYZ from origin and not from anything else? say put location here, location. Then here is 10, 20, and 30. And then okay, so now location is not used. Does it mean I need to do another let? Copy this, put it here, then change this to location and do another print line. And pretend that this is location because I know. Okay. Yeah, that works. That works, definitely, yes. But why can't I just put location here? Oh, I can. Oh, I can. I cannot. This is confusing. This is confusing. So it means I always have to do this line just to know that the XYZ belongs to location. Or is there any other way? Okay, so can we do? Let's accept this for now until we find alternatives later on as we go through the book, because ideally this is learning Rust firsthand. Just like you, I don't know how to program in Rust as well. So by watching my video, it means that we're doing this together. Or if you are doing this in your own Visual Studio Code, maybe you figured out how to do it well and good. Maybe you can post that comment in my channel also. And that will help me a lot as well. Yep. So once again, with an open mind, let's just accept that this is how we're going to destructure structured tuple. Yeah. Okay, let's move on. Okay, so unit like structs without any fields. You can also define structs that don't have any fields. These are called unit like structs because they behave similarly to parentheses. The unit type that we mentioned in the tuple type section, unlike unit like structs, can be useful when you need to implement a trait on some type but don't have any data that you want to store in the type itself. We'll discuss traits in chapter 10. Here's an example of declaring and instantiating a unit struct named always equal. Okay, always equal. Where is always equal? It doesn't contain anything. Let subject equals always equal. To define always equal, we use the struct keyword, the name we want, and then a semicolon. Struct always equal. No need for curly brackets or parentheses. Then we can get an instance of always equal, okay, in the subject variable in a similar way, using the name we defined without any curly brackets or parentheses. So looks like another shortcut. Imagine that later we'll implement a behavior for this type such that every instance of always equal is always equal to every instance of any other type, perhaps to have a known result for testing purposes. We wouldn't need any data to implement that behavior. You'll see in Chapter 10 how to define traits and implement them on any type, including unit-like structs. Okay. So it mentions something which we need to take a look in Chapter 10, which we wouldn't do now, otherwise we'll be distracted and I don't know how deep the rabbit hole will go. So let's see later on in Chapter 10. For sure there will be some purpose. There's a reason behind it. Okay. Ownership of struct data. In the user struct definition, we use the owned string type rather than the reference to a string slice type. This is a deliberate choice because we want each instance of the struct to own all of its data and for that data to be valid for as long as the entire struct is valid. Okay, so the intention is for its data to be valid for as long as the entire struct is valid. It's also possible for structs to store references to data owned by something else, but to do so requires the use of lifetimes. A Rust feature that we'll discuss in Chapter 10 again. Yeah, nice. Lifetimes ensure that the data referenced by a struct is valid for as long as the struct is. Let's say you try to store a reference in a struct without specifying lifetimes, like the following. This won't work. Okay, let's see. Now that we understood struct somewhat, the basic concepts of struct, so let's go through and read and interpret this one. So we have a struct user having a field active named as active using Boolean data type username. Okay, so as a reference to a string slice, email reference to a string slice, sign in count, and signed integer 64. Active takes on the value true, username. Okay, so string literal, username 123. So instead of the string with a capital S compound type, now it's using the string literal. Email, this one, okay. The compiler will complain that it needs lifetime specifiers. Okay, cargo run, username, expected name, lifetime parameter. Okay, so now because of this error, you need to jump to Chapter 10, which I don't want to do now. That will be a distraction. In Chapter 10, we'll discuss how to fix this error so you can store references in structs. But for now, we'll fix errors like this using own types like string. Yes, would use string for now instead of references like at str. So I don't want to complicate things for now. I would stick to what I know, string. Nothing wrong with that. I'm sure Batman would be happy. Okay, so let's move on. Next chapter, an example program using structs. To understand when we might want to use structs, let's write a program that calculates the area of a rectangle. We'll start by using single variables, and then refactor the program until we're using structs instead. Okay, let's make a new binary project cargo called rectangles. Okay, you already know how to do that. Come here, come out from this directory, cargo new. What's the name again? Rectangles. Rectangles. Rectangles with an S. Okay. So, no, code dot. Let's close the other window. Okay. That will take the width and the height of rectangles specified in pixels and calculate the area of the rectangle. A short program with one way of doing exactly that in our project. Good. Okay, let's copy this one. Okay. This is a scalar I32 signed integer by default, assigned to width or binded to width 1, height 1. Print line, the area of the rectangle is area width 1, height 1. Area is a function with, okay, now it's unsigned 32. Okay, so it's unsigned 32, height returns unsigned 32. How do we return the value? We can just simply put this statement without the semicolon with times height. Nice. So let's run the program. Area of the rectangle is 1500 square pixels. Okay. Yeah, same as this one. The code succeeds in figuring out the area of rectangle by calling area function with each dimension, but we can do more to make this code clearer and readable. Clearer and readable. Okay. I think it's already clear and readable for me. Let's see what else we can do. The area function is supposed to calculate the area of one rectangle, but the function we wrote has two parameters. And it's not clear anywhere in our program that the parameters are related. It's not clear anywhere in our program that the parameters are related. Not related. I mean, it's width and height. Okay. It would be more readable and more manageable to group width and height together. We've already discussed one way we might do this, the tuple type. Okay. Factoring with tuples. Okay. Rectangle. Okay, so it's done like this. It's a tuple, and then rect1 is passed here. And this is a tuple named dimensions, which is a variable. Okay, and dimensions Okay, so dimensions, the first value in the tuple, which is 0, times dimensions, second value in the tuple, 1. Okay, so let's copy this. It's okay. Of course, it will return the same value that is expected. Only thing we did here is, yeah, this was changed into a tuple. In one way, this program is better. Tuples let us a bit of structure, and we're now passing just one argument. But in another way, this version is less clear. Yeah? Do you agree? It's less clear. Tuples don't name their elements, so we have to index into parts of the tuple, making our calculation less obvious. Mixing up width and height wouldn't matter for area calculation, but if you want to draw the rectangle on screen, it would matter. We would have to keep in mind that width is the first index and height tuple is the second index, index 1. This would be even harder for someone else to figure out and keep in mind if they were to use our code, because we haven't conveyed the meaning of our data in our code. It's now easier to introduce errors. Refactoring with structs, adding more meaning. Okay, we use structs to add meaning by labeling the data. We can transform tuple we're using into struct with a name for the whole as well as names for the parts, shown in 5-10. 5-10. Okay, so now we have rectangle with U32, and then we instantiated rectangle with 3050, rect1. Rect1, we have the area function, then we are referencing. So we are borrowing. Rect1, rectangle, returns U32, U32. So we are borrowing rectangle dot width times rectangle dot height. And then we are returning it into somewhere in the scope when we are printing it. Then after which the value returned by area will be out of scope. Okay. Let's read. Rectangle. Inside the curly brackets, we define field width and height. Yes. Struct width and height. It's clear that we have width and height. Then we are accepting a reference to struct, where now we can use the field name width and height. Okay. Our error function is now defined with one parameter, rectangle, whose type is an immutable borrow struct rectangle instance. Immutable, so it cannot change. As mentioned in chapter 4, we want to borrow the struct rather than take ownership of it. So that's why we have the %. This way, main retains its own ownership and can continue using rect1, which is the reason we use the ampersand, ampersand, in the function signature and where we call the function. The area function accesses the width and height fields of rectangle. Note that the accessing field of a borrowed struct instance does not move the field values. Yeah, because it's a reference. Now uh, where are we? Does not move the field values, which is why you often see borrows of structs. Our function signature, okay, so it means that usually if you have struct here, in the function you put at sign reference so that we can borrow the values here. Struct will not own the value. So I think it's a pattern. Struct ampersand ampersand struct. Okay, where are we? Our function signature for area now says exactly what we mean. Calculate the area of rectangle using its width and height fields. This conveys that the width and height are related to each other, and it gives descriptive names to the values rather than using the tuple index values of 0 and 1. This is a win for clarity. Yeah, fully agree. This is a win for clarity. This is how we should code these things. Let's do this. Oops. Okay. Okay, so since we are borrowing, it means after this one, I can still do a print line just to prove that it's borrowing. This is rect one with one with equals this one equals this one. Yeah. So 30 and height is still there. You can still use rect one. Good. Okay. Adding useful functionality with derived traits. Okay, so now this one mentioned derived traits. It'd be useful to be able to print an instance of rectangle while we're debugging our program and see the values for all its fields. Print line macro as we have used in previous chapters. This won't work. However, there's this print line macro. Macro. Okay, so I don't understand this. It's quite advanced for now. This won't work. Okay, let's just continue. Okay, so if it's just rect1, so we cannot print rect1. Get an error, rectangle doesn't implement display. Yeah. It has to be rect.width. The print line macro can do many kinds of formatting, and by default, the curly bracket style print line to use formatting known as display. Okay, the curly brackets. By default, because there's only one way you'd want to show a 1 or any other primitive type to user. But with structs, the way print line should format the output is less clear because there are more display possibilities. Yeah. Do you want commas or not? Do you want to print curly brackets? Should all the fields be shown? Due to this ambiguity, Rust doesn't try to guess what we want, and structs don't have a provided implementation of display to use with print line and curly brackets placeholder. If you continue reading the errors, you'll find this helpful note. Help. The trait display is not implemented for rectangle. Note, in format strings, you may be able to use, I think we've seen this earlier, colon question mark or colon sharp question mark for pretty print instead. Let's try the print line macro. Call will now look like putting the specifier inside the curly brackets tells print line we want to use an output format called debug. The debug trait enables us to print our struct in a way that is useful for developers so we can see its values while we're debugging our code. Cool. Compile the code with this change. Drat. What is this? You still get an error. Rectangle doesn't implement debug. But again, the compiler gives us a helpful note. Trait debug is not implemented for rectangle. Note, add sharp derived debug to rectangle or manually implement debug for rectangle. Okay, so we have to do more things. So we do it like this and then we put something like this. Okay. Rust does include functionality to print out debugging information, but we have to explicitly opt in to make that functionality available for our struct. To do that, we add the outer attribute sharp derive debug just before the struct definition. Okay. Okay. So this is the right way of doing it. So let's copy this. Or wait. Let's copy this instead. Control C, go to first line, insert, E, debug. There's a space somewhere. What is this? Then here, let's comment this out. Insert. We have to insert this one. All right. So what happens here? Derive debug. Okay. Then rect1 question mark. That's wrong. Oh, rect1 is rectangle. Okay. Width 30, height 50. Rect colon question mark. Yes, I wanted to try array, so let's try let a equals to 1, 2, 3, 4, 5. And can we do a print line a equals like this, a colon like this, then it should print the array array and let's make it explicit array a Rate equals. Huh? It's not A anymore, so A underscore R grade. Okay, let's run. It worked. It worked. Nice. So take note, sharp derive debug. Can do something like this. Nice. Okay. Adding the attribute to derive the debug trait and printing the rectangle instance using debug formatting. Now when we run the program, we won't get any errors and we'll see the following output. Yeah, nice. It's not the prettiest output, but it shows the values of all fields for this instance, which would definitely help during debugging. When we have larger structs, it's useful to have output that's a bit easier to read. In those cases, we can use sharp. What's the difference? Sharp would, okay, so it's pretty formatting. I think pretty formatting, I've seen that somewhere. Cannot exactly remember where. So let's try sharp, and let's run that one. Nice. Okay, so let me try mm, I think I did something like this earlier. It will complain and there. Sharp question mark for pretty print. So if I do a colon sharp question mark, then we run it. Yeah. Rectangle. I think it will only work if we have this derived. Yeah, now it will complain. And it's here. Consider annotating rectangle with derived debug. Yeah, of course, it will only help if we've gone through the concept. Otherwise, starting out, we wouldn't have any clue how to do this. Or maybe this one. 2, 1. Yeah. Line 2. Row 2, column 1. Okay. Oh, does it mean, so because we have run and debug here, run and debug, derive debug. If, let's try something. So if I do a cargo run, but it goes under debug, see? So if we do a tree, yeah, you have, so it was compiling it, it goes into debug. Let's clear that one. Cargo, it help how to change it to release. Maybe cargo build help. Dash help. Release. Okay, let's see. Cargo build dash release. Okay, so it's release. Cargo run. No, cargo run will still run debug. We have cargo run for release. Cargo run options. Release is here. Okay, so cargo run release. Oh, still shows. So it means that this annotation it includes a debug macro, but it will show up whether it's you're building for debug or release. Interesting. How does it affect file size? Cat no, ls tr source, no, not source, target debug main rectangles. Okay, and we change this to release. Release is definitely smaller. How do we simplify this? tr release rectangles block size equals to KB, 426 KB. The other one is debug. Yeah, so that's 426 versus, how big is that? Let's put it in MB. I think it's in MB now. 4 MB. 1 MB. If we remove debug, then don't have this print line statements. But we have this instead. Of course, there will be a slight difference. So cargo build dash a cargo build, and it says okay, that is just a warning. Cargo build release. Okay, and then let's display debug. KB. 426 3685 versus debug release 426. Debug is 3685 versus 3707. That's a small difference. Let's see. Compare against release this and then debug. Okay, 3684752. Here's debug. 3684752. I'll release 425992. Here it's 425344. It's a difference. 425344 versus 425992. That's 500, around 500 bytes. Okay. Another way, okay, debug macro, which takes ownership of an expression as opposed to print line, which takes a reference. Debug macro takes ownership, while print line takes reference. Prints the file and the line number of where that debug macro call occurs in your code along with the resultant value of that expression, and returns ownership of the value. Note, calling debug macro prints the standard error console std error as opposed to print line, which prints the standard output console stream std out. Okay, error and out. You see that in chapter 12. Here's an example where we are interested in the value that gets assigned to the width field, as well as the value of the whole struct in rect1. So we still have the annotation, and then we have this one, debug 30 times scale. Okay, width is 30, and then multiplied by scale, debug. We can put debug dbg exclamation mark around the expression 30 times scale, and because debug returns ownership of the expression's value, the width field will get the same value as if we didn't have debug. Okay, because debug will return, it will take the ownership, so it means scale is not usable anymore because it's used by debug. So debug can return the value of this in width. Okay, we don't want debug to take ownership of rect1, so we use the reference to rect1 in the next call, and here's what the output of this example looks like. Okay, so you need a reference. Yeah, so we are just again borrowing. This is rectangle, which is a struct. We don't want to take ownership, so the pattern is we put ampersand here, so debug will print, while after this statement we can still use rect1. Okay, I mean it's not shown here, but we can try it out. Copy, show code, and let's clear everything here. Let's run this first. Let's see. Okay, 60 and 50. And then here, okay, we can do, let's apply what we have learned. Let's use print line instead. And let's do a formatting of question mark of rect 1. So we can still use rect 1 here. Yeah. Because debug doesn't take ownership of rect 1. If you remove this, rect 1 will complain because it's moved. So rect 1, we cannot access the values anymore. Okay. Okay, and then what else can we do here? Scale. Okay. So at this point, if we print scale, it will not allow us. What? Debug takes ownership. Okay, debug takes ownership of this expression. Okay, but what if I'll remove 30, I'll use scale here. What? You can still print scale. Scale is 2. I thought debug takes ownership. Debug takes ownership. No. Rectangle. I think we can still print rectangle here because 50 is okay. 50 is scalar. This is confusing. Let's remove debug and then put 30 here times scale. Still use scale. And still use scale. Why there's no error? Oh, why is it let's scale U32? That scale is immutable. Immutable, but if we delete this one, it still works. Okay, because struct would copy scale into width. Yeah, so this is copy, so it still works. Copy into width. Okay, so it means even if you have 30, okay, 30 scale is copy. Okay, so this is actually copying it to width. That's why it works. Then how about debug? copying it, and then debug will take ownership. What was that statement again? We can put debug around the expression 30 times scale because debug returns ownership of the expression's value. Ownership of the expression's value. So if it's taking ownership, does it mean that it's copying it to width? Maybe. Is there a way we can see this in memory? I think that would be better. But anyway, we have tried it out. It means we can still use scale here. I think width will have its own copy, and it's still okay to use debug here. Yeah. Even if you don't use debug, doesn't make any difference actually to do it like this. It is perfectly legal, unless if there's a difference. Yeah, scale is still 2, width is still 60. But if we comment this out and we do another one here, still perfectly legal because that's the intention behind struct. So as long as rect1 is within the scope, if you use structs, you can still get same value. Yeah, that's clear. Okay. What's in here? 3 scale, and its resultant value is 60. The debug formatting implemented for integers is to print only their value. The debug call on line 14 for outputs the value of rect1. Oh, I think we missed this part. Okay, cool. So it means debug here, once it is evaluated, it will print out something like this. Then it will not take, or what was that? It will take ownership of rect. In the next call, here's what we output. We don't want debug to take ownership of rect1. So we use our, okay, this statement is actually this one. Yeah, but the significance of this is in this line, it will print out like this, 60. It will take ownership 60 and bind it to width. So width now will have value 60. Okay, that's the difference. Okay. This output uses the pretty debug formatting of rectangle type. The debug macro can be really helpful, yeah, when you're trying to figure out what your coding is doing. In addition to debug trait, Rust has provided a number of traits for us to use with a derived attribute and can be useful behavior to our custom types. Those traits and their behaviors are listed in Appendix C. We'll cover how to implement these traits with custom behavior as well as how to create your own traits in Chapter 10. There are also many attributes than derived. For more information, see the attribute section of the Rust reference. Our area function is very specific. It only computes the area of rectangles. It will be helpful to tie this behavior more closely to a rectangle struct because it won't work with any other type. Let's look at how we can continue to refactor this code by turning the area function to an area method defined in our rectangle type. Okay, so before we continue, let's take a quick peek at this appendix C. So traits is like, okay, the way I understood it, it's when you're displaying, for example, it would understand how to format the display. Okay, so here display is being mentioned, programmer output, okay, 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 okay. Can skip this for now. We don't need to confuse ourselves. Then here, let's see what's in here. Attributes. Oh, sharp. Okay, then attribute. I think that's the debug. Derived debug here. Sharp. Outer attribute. Right? Oh, this is outer attribute. That's the syntax. Okay. So we don't need to worry about that for now. Let's move on to the next topic. Let's see how long is this method syntax. So other than struct, we can define methods. Okay, maybe let's do this in another day. I think this one itself is already quite long. I have to end the session here. Then see you in the next video. Yeah. Thank you for watching. I hope you've learned something today. Yeah. Bye for now.